last part of this PDE class, we talk about integral equation methods, and we have just as an outline of what we'll do in this section. I'm going to talk a little bit as an overview today. And the ones that, how many of you are aeroastro? I should ask the other way. How many are not aeroastro? So, because most of the students are aeroastro, and the thing that they mostly use for aerodynamics are what are called potential flow theory, and you're solving surface integral equations to calculate drag on aircraft, and because of that, we talk mostly about surface integral equations, but I'll also say some about volume integral equations for non-uniform materials, but not as much. So we'll talk a little bit about integral equation basics. So I'm going to give you the sort of the 15-minute, well, hour and a half version of integral equations today, which means I'll say a lot of things somewhat vaguely, not technically very formally, to give you kind of a framework of what the whole subject's about, so you can hang the details as we go through it. We'll talk next time about quadrature and cubature, so I'll give you a little bit of the theory of quadrature. Some of you have had an undergraduate numerical analysis class, may have seen some of these ideas before, and but I think you'll see them in this more linear algebraic context. You can more easily generalize them to newer methods. Then we'll talk about first and second kind theory, and probably the most important idea in this topic, which is the Nystrom methods. And these are the integral equation methods that pretty much everybody uses, and they turn out to be much easier to implement than other choices you might make by just sorting through the literature. And then we'll talk, after that we'll have most of the material we need to do, most of the problems on the problem set. I'll talk a little bit about formulating integral equations, then the potential theory, principal values, and something called the radiation condition. And then we'll talk about some other issues about what are called first and second kind integral equations. So when we mentioned in the early part of the course about second kind theory, we're not very clear about, so if this is second kind, what's first kind, and why is it harder? And I'll say a little bit about that. And in the last lecture, we'll talk about what are called fast solvers. And this is why everybody who's interested in integral equations is interested in integral equations. When we're done with today, you're going to think, well, I have finite element methods or finite volume methods, and they generate sparse matrices, which I can solve either iteratively or directly with fast methods. And I have these integral equation methods which generate dense matrices, which are formally n cubed to solve. Why would one ever do that? And the reason is because in the last 2 or 3 decades, fast solvers have turned those dense matrices into sparse matrices and brought those methods into very common practical use. So to try to give you all of that story in this one first class, I'm not going to do a perfect job of that by far. I'm just going to try to show you some of the main ideas and some of the simple intuitions to keep in mind as we talk about some of the more formal ideas. I'll talk a little bit about exterior versus interior problems. When you find elements or finite difference methods, you're often talking about interior problems. You have a domain, you have the boundary, you know what the values are on the boundary, and you try and figure out what the fields are in the interior. But there are lots of problems that are exterior problems. So figuring out what the temperature is in your aquarium based on the boundary conditions of what the heat flow is or the temperature on the surfaces is an interior problem. Throwing an ice cube in the ocean and trying to figure out how fast it melts, that's an exterior problem because the ocean is, to first order, infinite. And then we'll talk about test function selection at this time, and I'll say a little bit about some issues in 3D. But again, this is going to be fast. It's going to be a little vague, well, a lot vague. Don't try to get the precise details of everything. Here in this first class, it's to try to give you the structure, right? It's try to give you what are the big ideas, and I'll try to underline those carefully. But there'll be some things that look like important details, and if they are, we'll come back to them later. And if they're not, then don't worry that you didn't get them. But it's really helpful to have, for many of you, you've probably never seen integral equations before, certainly never seen numerical techniques for solving integral equations. So you need maybe a little context for what kind of things you're doing. So as I said before, so I'm going to have to put up with me pointing at the screen. They took away my green laser at the airport. My green laser pointer, and I said, see, it says it's dangerous. Don't take your laser pointer the other way. It was a nice green one, too. So I don't have it anymore. So you have the temperature in the tank. You know the temperature on the surface of the tank, or you know the heat coming into the tank, or you throw an ice cube into a large bath. And maybe what you want to know is, what's the heat distribution? So maybe you know the temperature on the tank, and you want to know how fast heat's coming into the tank. You can calculate the heat flow by getting, if you knew the thermal conductivity near the surface and the normal derivative of the temperature near the surface. So if you're doing this with finite difference methods for temperature in the tank, so suppose I have heat flow. I have a domain omega and a boundary gamma. And suppose I know the temperature on gamma. So what kind of boundary condition is this? Dirichlet or Neumann? Dirichlet. And you spell Dirichlet how? That way. I never remember whether it's an E and an L. It's frightening. Then, so suppose we have this problem. How do we figure out what the heat flow is? Suppose I have in omega, it satisfies Laplacian of some potential is equal to 0, and I have some thermal conductivity. How do I figure out what the heat flow is into this tank if I'm using finite difference methods? Well, the first thing is you set up a grade of using finite element methods. Then what do? How do you figure out what the heat flow is once you've set that up? You're going to need the normal derivative of the temperature at the surface. How will you get it? So you know what the temperature is at these surface points. That's given. How will you find the normal derivative of the temperature?
Using the interior points.
Yeah, you use the interior points and you take differences, right? You can get dt gamma dn using finite differences. Or if you're doing finite element methods, you can use the basis function and differentiate those to get the normal derivative. But that's the way you think about solving for this kind of thermal conductivity problem. For integral equations, we would do it a somewhat different way, and I'm going to try to show you that in a moment. So, all right, so we do heat distribution in the tank, we set up the finite difference grid, we solve for the temperatures everywhere and inside, and if we only want the heat flow into the tank, how many of those temperatures do we actually need when we do a finite difference method? If we're interested in heat flow, we only need the temperatures near the surface of the tank. How many do we have to solve for? Do we have any nice way of solving for just the surface temperatures? No, we got to solve for them all. All right, so that's one of the things about volume methods, like finite element methods or finite difference methods, is they require that you discretize the entire volume. That's one of the things we're going to be able to escape using integral equation methods. And the place where that becomes particularly annoying is when the domain for which you're trying to get the heat flow. So you're trying to figure out how fast an ice cube melts. It's a famous problem. It's one of the things they used to give to MIT freshmen. They would show up, and the big question would be, how fast does the ice cube melt? And about 10% of the freshmen at MIT would get it to within 10% of time interval, and the rest would have no idea. MIT gets an extraordinarily talented undergraduate pool. We can do it by solving the exterior problem. But the exterior problem is infinite in extent. How do we stop the mesh? At what point do we obviously can't fill all of the infinity with a finite difference mesh. What do we do instead? So I have an ice cube. I know what its temperature is. It's sitting in the ocean, which has a given thermal conductivity. And I want to know how fast the heat's leaving the ice cube. How do I answer that question with finite difference methods? Yeah?
So like a no flux, really far away, maybe.
Yeah, so no flux. So we're going to come back to this. This is one of those subtle issues I promised to come back to. If there's no flux, there's no heat leaving the domain. So how does heat leave the ice cube? Where does it go? Your suggestion's a great one, right? Somewhere you have to truncate the mesh. You just had two choices as how to truncate the mesh. You picked one, no flux. What was the other one you could have picked? Yeah, you could have made the temperature 0. It's far enough away. The ocean is like an isotherm. Eventually far enough away from the ice cube. The ice cube, you swim a mile away from the ice cube. The ocean still has, whatever it is, 37 degrees or whatever it's sitting at. It's not going to be affected by the ice cube. It's probably good enough to put a fixed temperature. But if you pick no flux, and I promise we'll come back to that, then you have this problem. And we'll talk about that later. But for the moment, let's think about, okay, so we have to do this exterior problem. We have to put all this exterior mesh, all these unknowns, so we get far enough away where we can say the temperature is a fixed constant. When all we care about are the values near the surface of the ice cube. It's like a lot of work. Well, there are lots of problems like that. Problems where what you are interested in is the surface quantities, and you end up having to calculate quantities in a body, either in the interior or in the exterior. For those of you who are aeroastro, which one do you always care about? Which surface quantity are you most interested? Well, two actually. What's
Drag.
one of them?
Drag.
Say again?
Drag.
Drag. So one of them is drag, right? So the air's flying through the plane's flying through the air, and you want to reduce the drag. What's the other one you care about?
Lift.
Lift. All right. So you can't do lift with potential flux, but you can do drag. Okay. So, but there are lots of problems like that, and I have a few. So, capacitance calculation. You have plates. You put a voltage across the parallel plates. And you want to know what's the capacitance, all you have to do is figure out the surface charge. Well, maybe those of you I'm an electrical engineer, so the first thing I think about capacitance is, here's one of these little airbag accelerometers. It's actually one of the early versions of the ones. That's the one. The one you're looking at is one of the early versions that's now. So if you ever, if you're graduate students, you can't afford a car, so you don't know what it's like to drive. But if you did, you'd have an airbag in your car, and it would have an accelerometer in it. That's one of these little things, and it's really important to know what the drag forces are, and you can compute these things. But again, it's a complicated surface, and all you care about are the drag forces on it. Well, that may not be all you care about, but when you're trying to figure out how quickly it will move, the one you're all very familiar with, although hopefully won't see more of those in the very near future. And this is the surface of an integrated circuit. So people who do capacitance calculations to figure out how fast a microprocessor is going to be, they extract capacitance as these very complicated geometries. It's hard to see here, but there are about 10,000 little green wires. They're all part of one interconnect. It's a signal being sent out in a microprocessor, and they use what are called fast methods to do these kinds of calculations. All of them are exterior problems. They all share this property. The MEMS, the aircraft design, the signal line. These are all exterior field problems. You care about the fields outside the conductor, outside the aircraft, outside the MEMS device. The quantities you're interested in are on the surface of the device. So on the MEMS device or an aircraft is drag, and the signal line is the surface charge, so you can calculate capacitances. And one more thing we need for these integral equation methods is the exterior domain has got to be linear in space invariant. So we're not talking about problems where the outside domain is a gradually, stiffening molasses. So it's like water near you, and it gets like molasses further away, and it gradually varies. We're not talking about problems like that. We're talking about ones where the exterior problem is uniform. So these come up a lot too, but not as much as you would think. And there are some new methods in this area for dealing with problems with spatially inhomogeneous material, but we're not going to talk so much about those. We only have about 6 lectures left, and so I have to pick and choose the topics. All right, so you have the tools you need to solve these problems. The problem is if you have an exterior problem, we're interested in the quantity in the surface. You have to fill the entire exterior domain with a mesh so that you can calculate these surface quantities. And it would be nice if you didn't have to do that. If you could somehow figure out the surface quantities by not filling the entire exterior domain with the mesh. So I'm going to give you an example of one, a relatively simple one. So suppose I have a circle. My domain omega is a circle. And it may not look like a circle, it's intended to be. And I know that the value on the surface, the potential on the surface, everywhere in gamma is equal to 1. What's the field everywhere outside? Can you tell me what it is? All right, so you're thinking, all right, so now I got to integrate over a circle, and you're thinking about some, trying to remember integration formulas. Don't. If we know outside the Laplacian size equal to 0, I can generate a solution, a potential that satisfies this. This is the differential, the PDE. And I can generate that solution by putting a point charge in the center. And if this were, instead of a circle, were, I'm actually going to think of it as a sphere, because I want to think about the three-dimensional problem, because you're more familiar with that. If this were a sphere and I had a single charge in the center, what's the potential due to that single charge? I have a charge at a point. Let's call this position x equals 0. What's the potential due to that charge?
Goes as 1 over the distance away from the charge.
Yeah, so if I have a position x prime, and this is at x equals 0, then this potential is q over what?
4 pi r sine pi.
All right, so now there's a difference between. So I'm more of a mathematician.
Some convention, yeah.
Yeah, so the 4 pi, I'm picking my units so that disappears. So we at some point we'll have to worry about the 2 pi's and 4 pi's, but not at the moment. So in some units, this is the potential. Is this correct everywhere outside? Does this satisfy the PDE everywhere? Well, so before we head on, let's look at a few slides ahead, because we have some of the details on the slides. So we have this point charge. If this were 2D, the distance would be just the log, there would be a log function instead of just this thing. So in 2D, this 1 over r that you think of, point charge, position outside. In 3D, it's 1 over distance. In 2D, it's this log of distance, which has a lot of counterintuitive properties to it. So I don't usually use that in terms of examples, but you should have in mind that the potential due to a point charge in 2D is the log of the distance between the point charge and the place you're measuring it. And the way you can see that this potential satisfies either in 2D or 3D, these potentials satisfy the Laplace's equation. How do you know? How do you know this satisfies the Laplace's equation? What formal theory do you appeal to know that it satisfies the Laplace's equation? At any point except where the point charge is? What would you do?
Plug it into the PDE.
You could plug it into the PDE, right? You could just differentiate it and see, does it actually equal 0? And if you do that, if you go ahead and calculate the derivatives and add them up in 3D for the Laplace's equation or 2D for the Laplace's equation, you'll see if you laboriously differentiate it, and this is something that you should do sometime eventually to convince yourself that it really does work out, because at some point, you know, the fact of the mathematics just works, and whenever distance turns out to satisfy the Laplace's equation, you wonder, so how did they come up with the Laplace's equation in the first place? And did they think of the Laplace's equation and then discover that point charges produce solutions to the Laplace's equation? Or did they think about point charges and then come up with the Laplace's equation? Well, that's Laplace. But given that, That's not exactly the solution to this problem. What have we left out? So we now have, by the potential to this point charge, Q over x prime gives me the potential everywhere outside that sphere. What's its value exactly on the sphere? Does it match my Dirichlet boundary condition? Well, what things do you need to know to figure that out? I say Q equal to 1. Does that mean it matches potential at the surface of the sphere? What are the points on the surface of the sphere? What values of magnitude of x prime do they have? Is it a big sphere? Is it a little sphere? What number do we use to characterize whether it's big or little? Radius. So if we knew the radius of the sphere, could we figure this out? If we knew the radius of the sphere, if r is equal to 10, can you tell me what Q is so that you get a potential that satisfies the boundary conditions and the PD by picking a certain Q? And what value of Q should that be? Because that says that psi at Q over 10 should be equal to 1, which means Q is 10. And that satisfies the boundary conditions. So if we have a solution that satisfies the PDE everywhere outside the sphere and matches the boundary conditions, are we done? Do we have a solution to the Laplace equation? Could there be another one? Well, for the moment, if we assume something about what happens at infinity, and this is one of these subtle things that you happen to trip over in answering the question the first time, that I'm not going to answer yet, but we will come back to. But for the moment, we can think of as long as the potential goes down to 0 at infinity, then we have a solution, right? This potential goes down to 0 at infinity. It satisfies the boundary conditions. So you give me any exterior domain. It has a surface. I put a point charge in the middle of that domain. It produces a solution that satisfies Laplace's equation everywhere in 3 space. And I just set its value so that it matches the boundary condition. Is it going to work? You have one example, right? It worked really well in the sphere. What if this weren't a sphere? What if it were an egg shape? Would that still work? What would go wrong if instead of a sphere I had an egg shape? And I said the surface on my egg, an ellipsoid, surface on my egg is unit potential, and I want to use this formula. Will I get exactly the same potential from this formula? Will it work for an egg? So it works for a sphere, but it won't work for an egg. Will it work for the surface of a bottle? Surface of an airplane? Well, so we have this idea, right? We put a point source in the interior, which is outside the domain of our interest. Our interest is the outside problem, the exterior domain. We put a point charge in the interior, and we can generate a solution that satisfies the Laplace's equation. And that's great, except for this problem of the boundary conditions. So it works really well if we put the point charge in the center of the sphere and our domain is described by the surface of the sphere. Now, we're publishing the math journal, that would be sufficient. But we are not. We are engineers and we actually have to solve real problems, which are not, unfortunately, spheres. Very few, for example, spheres will fly unless they're filled with hydrogen or helium. What do we do now? So we have a square set. Yep.
Could we transform our problem so that it fits into a sphere? So a ellipsoid, you could just transfer.
So that's a great idea. And there are all these techniques based on doing variable transformations to try to turn it into a sphere. It's really hard to come up with a transformation that takes an F14 into a sphere. It's a hard problem to do that transformation. But it doesn't mean there aren't lots of techniques for problems like this where you use that. There are problems that, so it's a very good technique. Trying to come up with those transformations, particularly in 3D, is hard, but that doesn't mean it's not a good idea. But we're going to need something that maybe isn't so sophisticated. So what else? What if we put a second point charge in there? Is the potential due to 2-point charges? Does that also satisfy Laplace's equation? If Laplace's equation has what property that means if I have one solution to Laplace's equation and another solution to Laplace's equation, their weighted combination is also a solution to Laplace's equation because Laplace's equation is linear. All right, so, but if we have two, so we know how to do a sphere with one charge. Now, if we were doing really a 2D problem and had the logarithmic Green's function, we could do the same thing, right? We can figure out what the magnitude of the point charge is just by making sure we matched the one boundary condition we have at this radius r. So provided, we didn't just have to have a surface of the sphere, we also had a surface of the sphere where the potential is uniform on the surface. So that's really a very tightly constrained problem. But if we have an arbitrary surface with an arbitrary set of points, and now I'm going to start writing these things down in 2D. And in fact, some of the problems are done in 2D because it's just a lot easier to visualize 2D. But I warn you, these logarithmic Green's functions, they're really hard to get your head around because it means you're talking about problems that are infinitely long. And when it comes to electromagnetics, that makes some degree of sense. If you're talking about a flying aircraft, I don't even know how you think about an infinitely long flying aircraft. I don't know what these 2D things mean. So it's hard to develop intuition in 3 space, but it's much easier to write the equations down. So, we're going to look at things like that, but if you're trying to sort of intuit them by thinking of flow problems, thermal flow works okay. But it's just, I always find it a difficulty, even though it's much easier to write down problems and do examples in 2D. All right, so suppose we now have the potential as a weighted combination of these potentials due to point charges. So we have each point charge is at some different location in the interior. We're going to sum over all those potentials due to all those point charges and a log in front of it with a weighting coefficient. We're going to sum those all up, and they're all going to be, we're going to start referring to that logarithmic function in 2D or 1/r in 3D as the Green's function for Laplace's equation. For most of this, we're just going to be doing Laplace's equation. If there's some time, well, with 6 lecture, probably won't do much other than Laplace's equation. But for this, just so we don't have to keep writing down 2 in 3D or the square root of the sum of the squares, we'll write it down as a Green's function. Now what we can do is to say, well, if I put enough point charges down, I can write down a system of equations. I have these points, so I take my domain, I sprinkle point charges in there, a bunch of them, and then I'm going to pick the magnitude of these point charges to match the boundary conditions. So where should I match the boundary conditions? How many boundary conditions can I match? If I put 100 points inside that square, how many points on the surface of the square can I match? Well, I have 100 degrees of freedom. Is the system of equations I'm going to get? Exactly how do I set that up? Well, so let's imagine that we have some green test points on the surface of the square. So we're going to write down something that takes us from these point source weights that's going to be alpha 1 through alpha n. We have this matrix that's going to be number of point sources by number of test points. And we're going to set that equal to, if we have a Dirichlet problem, we're going to have a set of potentials at these test points. And then we have to decide how many test points. Well, if we have n weights, how many test points should we have? So you say, well, n. Why n? Why as many test points as I have weights? What will be true about the system of equations? It'll be square. Provided, so we ought to be able to invert this. If we had more test points than we had weights, point sources, we'd get a least square solution. We could do that too. In MATLAB, you can't even tell. You just use the slash command. It takes care of it for you. So, but from your program, it doesn't really care whether you have more test points or fewer test points than you have weights. So there are lots of different methods for doing this, but for the moment, we're just going to think that we have as many weights as we have test points, but this is not fundamental. And what goes inside of here is this Green's function that goes from point source location xi to test point location xj. Which is which? Which is the test point, which is the source point? For Green's functions and Laplace's equation, does it matter? Yeah, so Laplace's equation, we always have the idea that it's symmetric. That is, if I have the point source in my right hand and my test point in my left hand, the interaction is the same as if the point charge is my left hand and my test point is my right hand. Whenever distance doesn't care, you know, which way the distance along a road doesn't matter where you start. Okay, so how well is this going to work? And what things have we figured out yet? So we have n point sources, n test points, and then we can set up a system of equations, and once we get the weights, can we get the potential everywhere outside? Once I've done that, can I only get the potential at the test points, or can I evaluate it anywhere outside?
Anyway.
You can evaluate it anywhere. I just pick a point x, and I sum up n contributions from these n source points with the distance to this test point. So I now have actually a representation as a weighted combination of source point potentials. That weighted combination of source point potentials tells me the potential everywhere. What if I wanted the normal derivative, or the derivative in any direction? What would I do with those point sources? So they produce potentials either like 1 over r in 3D or like log r in 2D. If I want to know what the normal derivative is, the potential is at any point in the exterior, can I do that? I just differentiate the Green's function once. And now I have a weighted combination of differentiated Green's functions that I can use to calculate the normal derivative anywhere. So I have an ice cube, I throw it in the ocean. I represent the ice cube with point sources. I calculate what those point sources are. And then I have a representation of the potential everywhere outside that I can differentiate and actually figure out the heat leaving the ice cube. This is not what every freshman that goes, or half the freshmen who come to MIT do. They have other approximation schemes, including throwing an ice cube in a bucket of water and timing it. Okay, so we still don't know two things. What two things don't we know? So I said put test points on the surface and put source points in the interior, and just set the weights for the source points in the interior so that they produce a potential that matches the given potential at the test points. But I didn't say what. Where should I put the test points? Where? Where should I put them? Spread them around. What should I do with the source points? Should I cluster them in the center? Should I move them to the edge? What happens to the potential to one of those sources when you get too close to it? What does it do?
Diverges.
Well, it diverges in a particular way. What does it do? If I get too close to a point source, what happens? The the potential goes to, the field goes to infinity. So that may be what you meant by divergence. Yes, so it goes to infinity. Numerically, that might not be such a good thing. If some of your matrix elements are really close to infinity, and others are like 1, it's not so good. So we have this problem now. Where should we put the sources? We could put them near the edge. The problem with putting near the edge, then every test point will have a point source that it is affected by most strongly. So their distance apart will be very small, and that entry in the diagonal matrix will be near infinity. And all the other points won't matter very much. So we might get large errors if we do that. So that might say, don't put the points too close to the edge, because then the interactions get too large. What if I cluster them all in the center? Could anything go wrong there?
Not leverage.
Say again?
No, not leverage over any given degree of freedom.
Yeah, so you're right, and I'm gonna make you be a little more precise about what you mean by leverage. So if I pull off one of those points and say, how does it affect all my test points? And then I pull off the point source right next to it and see how it affects all my test points. Those 2 point sources, when I cluster them in the center, are going to have almost identical effects on the test point. What will that mean about the system of equations we generate to solve for the test point weights? So I'll have one row, or one column rather, corresponding to one test point, another column corresponding to a test point right next to it, and those columns will be almost equal to each other. What does that mean about the system of equations when the columns are almost identical? Yep.
We're very close to not being linearly independent.
Not being linearly independent, which means the matrix is ill-conditioned or possibly even close to singular. If it's ill-conditioned, then that too will cause you problems. It means that you will get, if the matrix is ill-conditioned, you may have test point values that are 1s and 2s, and you may get these weights, being 10 million or 100 million. So you have one weight is 100 million, the other one next to it will be minus 100 million. And then you'll get weird errors because of that. So these methods, they have all these different names. They're called desingularized methods, they have all, I forgot, there's a whole bunch of different names for it. The problems with these 2 placements are, if it's close to the boundary, then what happens is at the test points, you get finite values, and then in between the test points, the 2 point sources don't exactly cancel out, and you get these things going to infinity, and if you cluster them in the center, the matrix becomes singular. Both of them produce problems. So I wanted to show you, but that doesn't mean you can't use these methods. And in fact, there have been renewed interest in these methods because there's some new algorithms for figuring out how to place these points in good positions. But I just wanted to show you a computational result just so you have an idea in mind of the way the errors form from these methods. So the neat thing about them is this. No matter what you do, wherever you put the point sources, wherever you put the test points, however ill-conditioned the matrix is, the solution you get, does it always satisfy Laplace's equation? And so you're constructing a solution that always satisfies Laplace's equation. So very different from finite element methods, finite difference methods, where those solutions don't always satisfy the PDE. These always satisfy the PDE. What they do is satisfy the boundary conditions. So if you do these kind of methods, you definitely satisfy the boundary conditions at certain test points and not in between. So yes, you produce a solution that satisfies the PDE, but if you don't match the boundary condition, they can be quite far off. And when you're looking at these things that look like crowns, they're plots of the potential on this circle in between the test points. So you can see at the test points, the potentials are exactly 1. So we set the potential on the circle to be exactly 1. And then we put these source points, the ones in red, just inside, and then set up the system of equations and calculate it with n equals 20 and n equals 40 points. It's a little hard to see from here, but the error for n equals 40 is a good factor of let's see, it's about a factor of 5 down from n equals 20, or roughly a factor of 4, actually. But in addition, you see that the worst case errors are in between the test points. So right at the test points, it gets exactly the right potential for the surface. And in between the test points, it's not matching the boundary conditions. So, and then you go outside and then, well, what do you know about the errors in Laplace's equations? Where, do you know how many of you know the maximum modulus principle? Right, so here's the thing to know about Laplace's equation. For Laplace's equation, if you have something that satisfies Laplace's equation, and you have two solutions to Laplace's equation, and it's over a domain, and you know where the surface of the domain is, where's the worst case error? When it's an interior and exterior problem, the worst case error is always on the surface. So the difference between the two of them will never get worse than it is at the surface. So because of that, if you know what the errors are on the surface of this exterior domain, the errors always go down. The difference between the exact solution and one you might numerically compute, as long as they're both solutions to Laplace's equations, the maximum error is at the boundary. This is a great thing about Laplace's equation. It means that when you do these integral equation methods that look at surfaces, you only have to look at the errors on the surfaces. All right, so, but that's kind of a thing we're going to change, and one of the things we'll come back to and look at a lot. But we can get a lot of intuition from those kind of point source methods. But what we really do is smear the point sources into a density. So imagine you have these point sources and you put them in a crucible and you smash them up and you turn them into kind of a smear which you put on the surface. So now you have this kind of charge density smear on your surface. And since it's not a point charge anymore, the closer you get to the surface, the less actual charge there is. So there's a finite charge density. So if you're, unlike a point charge, which has an infinite charge density right where the point source is, this smear has a finite charge density. So it doesn't produce these infinities, but it replaces writing down these sums of point source potentials with an integral. So now you may all recognize the superposition integral, but if you have charge on the surface and you want to know what the potential is everywhere, you integrate that charge on the surface over the surface of your domain, and that gives you the potential everywhere outside. So now we're going to try to estimate the charge density. And that's the next step in this thing, which is, okay, so if we're talking about 2D, we're going to write down a system of equations where we have this charge density on the surface, it produces a potential, and now we want to know what that charge density is. We know what the Green's function is, we want to figure out what this charge density is. So that's a continuum charge density. With a continuum charge density, when we come up with the numerical methods for computing it, what's the first thing we do? So in this class, what have you done? You come up with some representation for that continuous density in terms of piecewise polynomials, finite elements. You call these things a term basis. All right, so we're going to come up with, so what's a good basis for this? How should we represent this continuous charge density on the surface? So we had point charges, and that was easy. We could just sum up the potentials due to point charges. We could get this matrix, we could write it down. So now we're saying, okay, well, we don't want to use point charges because the potential due to point charges go to infinity. We're going to use charge density because you get close to charge density and it doesn't go to infinity. And now we have to figure out, okay, if we're putting a density, it's like we're coating the surface with cream cheese or butter. Well, I think charge density is like. It's actually more like molasses. It's a joke with charge density. Just don't want you going out there and thinking, well, this electrical engineering professor said that charge is like molasses. Okay, so what's a good representation for the charge density? What should we use? So if we're talking about 2D, what's the surface of a domain in 2D? It's just a line drawn on a piece of paper. It's this curve. Right? So we're talking about this line charge. How should we represent this line charge? It's going to be distributed now. Well, you could use straight piecewise constant charge densities. So these are piecewise constant line charges. This is going to be our basis function. But we're going to, and this is one of those subtle points that people write lots of papers about, that we're never going to come back to, because it never matters. Well, it never matters a lot. It matters a little. We're going to think of when we do this. So if I'm talking about a golf ball, and I try to do the 3D generalization of this, which is flat panels, I'm going to say, I'm going to represent the sphere as if it's like a golf ball. Golf's maybe not such a good one anymore. It used to work 30 years ago, right? The golf balls have these sort of facets on them. But you think of it as like a polygon. So we're making a geometric approximation along with assuming that the charge density is constant along these lines. So we're going to say on each of these lines the charge density will be constant. So you may be thinking, wait a second. I started out with point charge, and I get too close to the point charge and it goes to infinity. What about a line charge? You get too close to a line charge, does it go to infinity? Turns out no, but you have to actually go through the calculation to see that. In 3D, you use sheets of charge, and sheets of charge of a finite charge density don't go to infinity as you approach it. But we're going to look at that a little more carefully, but not most likely today. And this kind of geometric approximation, it's not like integral equations the first time that you've seen something like that. You start representing spheres with triangles, you have the same sort of thing, right? The triangles that you use for finite, you do 2T finite elements of triangles, you get the same sort of thing. You are approximating, you know, a curved surface with piecewise constant straight sections, or you might use curved basis elements. And you can try to improve this, but we're not going to worry so much about that. And now what we're going to do is we're going to write down our integral equation as the Green's function is still the same, because that just is about the PDE. And we're going to use this weighted combination of line charges, and we're going to use that to calculate the potential. And now we have this other question, which is, so we took our domain, right? We started out this way. All right. Apologize for reusing the board, but I remember the camera's only pointing at these and not the other two. So we started out, here's our sphere, and we maybe put point charges inside. And we had test points on the sphere. And now we're going to replace that with these piecewise constant straight sections. It's supposed to be like a sphere. A sigma 1, sigma 2, sigma 3, etc. Those are the replacements for my point charges for my sphere, which you can see clearly goes through these points. Where do I put the test points? So I now have, well, how many unknowns do I have? I break it up into n lines, n piecewise constant lines. 1, 2, 3, 4, 5, 6, n. How many test points do I need to get a score system? I need n test points. Where should I put them? Should I put them at the ends or in the middle? Should I put them here? Or at the ends? The X's or the O's? How many say X's? How many say O's? Oh, well, this is how you get Trump for president. Well, so X's seem like a good idea. They're in the middle of the lines. But what about the endpoints? Maybe they seem a little extreme. Oh, I know, I'm sorry. Being recorded too, I'll have to bleep it. So, why the midpoints and not the endpoints? Well, there are a couple reasons. Something is, of course, at the endpoints you now have this sort of sudden inflection. But the endpoints are actually on the sphere. So it might seem like that's a good idea. What about in 3D, where I break the surface up into triangles? Can I use endpoints then in 3D? Will there be as many endpoints as there are centroids of the triangles? I imagine taking a sphere and turning it into polygons, with things with triangulations. Will you have this right number of points and unknowns? Well, you will if you put the point in the center of the triangle, because then you got 1 point per triangle. You put it on the vertices, not so clear. So in 2D you can do either one, in 3D, center. But it turns out there's some other advantages to putting things in the center, which is that you usually get better accuracy because it's a midpoint rule. It tends to cancel out linear variations. But again, for the moment, not the important part for us. So this is the idea. We're going to try to take our original problem, which has a charge density on the surface. We're going to try to calculate that charge density by making sure it produces potentials that match the given potentials on this surface. So we generate these piecewise constant representations of the charge. And we'll just integrate them. And what we have to do is to calculate these line integrals. And it's sort of a pain in the neck, but it's not that hard to do. But one can. And you set up a system of equations. So this is the idea. Now you have a 2D method. You pick a set of points on your surface in 2D. You take this curve. You connect the points with lines. Those define your line charges. Then you calculate the weights of the line charges by making sure it produces the correct potential at all of the test points. And you just have to be able to evaluate this Green's function, which is the integral over a line charge of the potential at these test points. And then once you have those weights, what can you do with them? Now I have this weighted combination of line charges. What can I do with that? Can I evaluate the potential outside? Yeah, I can use the weighted combination of the Green's function to evaluate the potential outside. Can I evaluate the derivative of the potential outside? Sure, I now have an analytic function for the potential everywhere outside. I can differentiate it, calculate flows, anything I want. So it's a numerical procedure that only counts on us being able to calculate the integrals of 1 over r over lines, which seems like a relatively simple problem. Turns out it has some subtleties to it, but I'll talk a little bit about this towards the end, and we'll talk about more tomorrow. Wednesday. All right, so now I have this question. Is that the right thing to do? Should we make sure that we pick the weights on the line charges so that they give exactly the right potential at test points? That seems like we're just sampling at test points. We could also do something else. What do we do in finite element methods? What do we try to do? How do we pick the weights for the finite elements? Plug it into the weak form of the integral and make sure the residual is what? All right, so Professor Wang's out of the room. One thing to remember about finite elements. It's the most important thing. That idea. The really great thing is for those finite element basis functions, you plug them into the integral operator, into the weak form, and you calculate the weights so that the potential it produces is orthogonal to that basis set. And we refer to that sometimes as the Galerkin method. Very powerful idea. But it's also a representation in a certain space of the PDE. We can do the same thing for integral equations. The difference is the theory for partial differential equations is probably one of the few places where this is true. The theory for partial differential equations is much easier to get at than the theory for integral equations because you have this projection on the surface and you get these what are called fractional sublow spaces. So we're not going to do very much of that. But there is something amazing about this when you do this. So we have two problems, and I'm going to say what this is in a moment. But so we have these two ideas. We could pick the line charge weights so that we get exactly the right potential at the test point. Or we could make them orthogonal to our basis. We could make the errors orthogonal to our basis. If our basis are lines, then we're basically saying the average potential on the line is right. So it can be off everywhere, but it's an average, it's right. And that's usually called the Galerkin method, and then you can come up with all sorts of variants where you come up with test bases and representation bases, and you mix them up in some ways, and then for certain kinds of integrals, it's really important to do that, but for the Laplace's equation, it's usually easiest just to think about the Galerkin method, where they're both the same. All right, so if we do this, we do collocation, where we have test points and the weights on the basis function, we get this matrix that relates the test point potentials to the weights on the lines. And there's something sort of weird when we think about these two methods. So we got one that says, I calculate the potential to this line charge, and then either integrate it over this other line charge, or I just test it to the center of this other line charge. So I have kind of two things going on. And let me just write a picture of that so we can sort of keep it in mind. So we're saying here are our line charges, and we're saying here are our test points in the middle, and we're saying this line charge goes to this test point. Sorry, I want something more compelling. Suppose my line charges are like this, and like that. So I have this line charge, and it goes to this test point. And I also have this second line charge going to this test point. Or, I take the same thing, I think, and I have the line charge, the big line charge goes to the entire little line charge, and the little line charge goes to produce potentials across the big line charge, and one of these is, as the x's, this is collocation, and the other one is Galerkin. Looking at those two methods, can you tell me something about the matrices they'll produce? So one is calculate the weights of the line charges based on making sure you match the test point potentials. The other one is calculate the, so that was this collocation idea. And the other one is calculate the line charge by calculating potential produces over the other line and integrating. So the problem with collocation is that I have one big line over here and a short one here. One big line, which is my right arm, and the short one, which is the yellow chalk. Is the interaction, is this right arm line charge and its potential, the potential produces this test point in the middle of the yellow chalk. Is that the same as the yellow chalk's line charge and its influence on the potential in the center of my arm? Are those two interactions the same? Right line charge really big. Test point potential in this little chalk. Little chalk and its influence on the test point potential in my much larger right arm. Are those two interactions going to be identical? No. But the Green's function has a symmetry, but the discretizations doesn't seem to capture that. So there's something funny about these collocation methods. What's going to be true about the matrix that you generate to calculate these weights then for collocation using test point potentials? What property will it not have? It will not be, begins with an S, ends with metric. It's not going to be symmetric. But the Green's function is symmetric, so that seems sort of odd. But if we instead of using instead we do a Galerkin method, where we say now we're going to take the potential due to the line charge and test it by taking its integral over the other line. So now I'm taking the potential due to my right arm and integrating it over the yellow chalk, and taking the potential due to the yellow chalk and integrating it over my right arm. Both interactions are going to be identical. You can just see it from the integration. So the Galerkin method for these problems, because the kernel or the Green's function is symmetric, the Galerkin methods preserve that symmetry. So there's something very appealing about that. In fact, it's the way in which you make energy arguments, just as you do for fundamental methods when you have what you refer to as self-adjoint operators. Okay, so nevertheless, so it's, it seems clear that it's better to use Galerkin methods, and so we should all use Galerkin methods, except of course that means you have to do this extra integration, which, when you're writing the code, you say, oh yeah, I'll do a single point in the center of the line as kind of a simple quadrature scheme, and I'll get around to doing the rest of them later, and later never comes. So people use collocation all the time, but Galerkin's better. Yep.
Can you repeat the difference between collocation and Galerkin, please?
So collocation was the one where I have the line charge, and I calculate the weights on the line charge by making sure it matches test points in the center of the lines. That was collocation. And Galerkin was I calculate the line charge weights based on making sure that it produces correct potential averaged over the line. All right, so we have now a whole collection of different things. Regardless of which one you use, all right, so what do the residuals look like? So here's a quick picture if you want to. So here's an answer to your question that's a better thing, which is a picture. All right, so for Galerkin, the test functions and the basis functions are, the basis functions for collocation and Galerkin are the same, the representation of the source. But in collocation, the test functions are like impulses. And in Galerkin, they're averages over line charges. So is that maybe a better picture for what the difference between the two is? But regardless of which one, well, now you can also think about what the errors look like. So in the residual for the collocation methods, the residuals go to 0 at the test points for a collocation method. So you have this nice thing where you get exactly the right boundary condition at a set of test points. That doesn't mean you get the right answer anywhere except those test points. But in the Galerkin method, your residual, your errors in the boundary are sort of averaged over each of these lines. So one is it's exactly right at certain points. The other one it's never right. So does that mean, what does that mean for the potential outside? So remember, both of these things produce solutions that satisfy Laplace's equation everywhere outside. It doesn't matter what the weights are, you still satisfy Laplace's equation. So these methods are just telling you about errors at the boundary. It's how poorly you satisfy the boundary condition, and then that gives you an idea about how big your errors are. All right, so so I don't want to start that. I want to say one more point about this because it's more important, and then I'll say a little bit about 3D problems. So I'll come back to this, but I just want to make sure I've made this point. These matrices, what's true about these matrices? Does every line charge affect every test point? So if I write down this A matrix that goes from alphas 1 to alpha n and gives me test point potentials, is this what's true about this matrix? Does every line charge contribute a potential every test point? So what's true about this matrix?
It's not sparse.
It's not sparse. It's more than not sparse, it's dense. But Galerkin method, what about Galerkin method? Is it better? Does it generate a sparse matrix? Does every line charge contribute to the average of the potential every test line? It does. So what does that mean about the Galerkin matrix?
It's dense.
Sparse or dense?
Dense.
Dense. So how many of you remember offhand, if I'm doing a 2D Laplace equation with a finite difference matrix with n unknowns, n points in a grid, how does and I solve it with sparse Gaussian elimination? Do you do this one? Do you know what how long it takes to solve? So if I have n degrees of freedom in an integral equation method, what does it take to solve the system? And just do Gaussian elimination is going to take n cubed operations. If the matrix is a typical sparse finite difference matrix in 2D, anybody know what it is for sparse matrix factorization? Yep.
And
Not quite n. It's an iterative solver. It's n. It's n to the 3 halves. Right, so, and there are a number of different ways of thinking about that. We usually use iterative methods.
Just did multi-grid last 2 lectures.
You did that. All right. So then so you have an order n way of doing it. So here's one thing that is interesting though about these dense matrices. What do you think happens to the condition number of those matrices as you refine the discretization? Versus so what happens to a finite difference matrix when you refine the discretization? If you make it finer and finer and finer, what happens to the condition number? How many iterations do you need to get, say, a conjugate gradient algorithm to converge before you do multigrid? Goes up and up and up, which is why you had to do multigrid. These matrices, we'll see. Their condition number remains bounded. It's an amazing thing. It means you can use a neuter solver. So we'll come to that. I want to at least point to a few of these things. All right, so I want to say 1 or 2 things about 3D problems, and I just want to show you pictures. So one of the very early uses of these kind of surface integral equations were to assess wave loads on ship hulls and tension link platforms. It's actually used to Newman, who was in our ocean engineering department, who retired just a few years ago, was like the world's expert on doing these things. So now you have a ship hull, and now you're going to take the surface and you're going to represent it with something. You can, if it's 2D and you have a curve, you can connect it up with straight lines. In 3D, you have to connect it up with panels, and if you try to keep all the points on the panels in the same plane, you get what are sometimes called, and that's because the panels don't actually connect up to each other, there is the term called leaky panels, because they used to use them for ship hulls. But they would have gaps between them. But if your surface is like a cube, you can just discretize the surface. So we can do a 3D problem, even though we're talking about mostly 2D. Then instead of lines, we have panels. We calculate we have the representation as point charges on panels. We calculate the potential by integrating over those panels. And we set up a system of equations where we put collocation points on the center of each of our panels. We have as our unknowns the charge density on each of the panels. And we solve for the charge density, and now we have a surface charge representation, which we can use to calculate the potential anywhere we want it. And one of the difficulties is that you have to calculate this integral over a panel of this 1/r function and evaluate it at test points. And as long as the panel is here and the test point is here, that works fine. But if they get too close to each other, like if you want to calculate the potential on a particular panel, if you're close by, you can sort of break it up into 4 panels and do it that way, and treat it as point charges, so you can do approximations. But the problem is, what happens when you have a panel and you have a point on the panel? So here's the question. Is the integral over a panel of the source of the charge on the panel, does it produce a potential on the panel that's infinite? As I approach it, so here I am at my test point, and I'm coming close towards the panel, and I land on the panel. You know, if I'm a bug, do I get zapped? Does it go to infinity? What do you think? No, it doesn't go to infinity, and a quick way to see that, you can just carve a disk out of the center of the panel and say, okay, well, I'll carve a disk out, now I have a panel. You have a piece of paper I can borrow? No, all right. So we're gonna do this. And we'll come back and talk about this a little more tomorrow. So we're gonna do this. We're gonna say, we're gonna carve a circle out of the center of the panel. And we're gonna say, so here's my panel now with a hole cut in it, and my test point is here. So the charge on the rest of the panel, it's not gonna produce an infinity on this point, because it's far enough away. The problem is, what does this thing do? Well, but this thing is a disk. And now you can use a coordinate transformation and actually evaluate that integral analytically. And you discover it's finite. So for sure, this is kind of an interesting thing, right? You have this, you start out with point charges which generate infinity, and now you have this thing where the potential, as you go towards the panel, it goes to some finite value, and then goes back down again. All right, but it is finite as you get to the panel. It also has to jump. Why is that? So I have a panel with, say, positive charge on it. I know the potential has to go up and then back down again. Why does the sign of the slope of the potential have to change signs? If I'm over here, which way does this field point? Which way does the field point on the other side? In the opposite directions. So you know it has to look something like this because it's got to change slope. So what if we differentiate that potential right at this panel? Well, then things are going to get a little weird. And we'll come back and talk a little bit about that too. All right, so how does one calculate this term? There are a whole lot of different methods, and we're going to talk a little bit about that next time. For this course, we have a code that calculates these integrals analytically. It's not that interesting a thing to do it analytically. It used to be. And as I said, the fellow who recently retired would hate me if I said, it's not that important because he was like an expert in calculating these integrals, using some very fancy theory and geometry to do general panels. But we're gonna have an analytic way of doing it, but we're also gonna talk a little about numerical ways of doing it, because the ones you can do analytically are for flat panels, and the world is not, in fact, flat. Something we've known for actually quite a number of years. All right, so I wanted to summarize. So there's a lot of things. We went from starting with integral formulations of exterior problems, starting with point sources, and noticing a really important set of things. One of them is dense matrices. So dense matrices, n cubed to factor, why would you ever use these methods? And from 1950 to 1990, that was the reason everybody used finite element methods. And then somewhere in the 90s, fast methods were developed, and we'll talk about them, but not till the end of the term. So I'm going to ask you to suspend disbelief and say, well, okay, we're going to do integral equation methods, and then you'll tell us that we can actually solve interesting problems with them at the end. We'll find some order n ways of solving certain kinds of problems with these methods. And we talked about these standard collocation and Galerkin methods, and we talked a little bit about these problems in 3D. So next time we're going to talk about calculating these integrals, and we're going to come back and look at these integral equations. And believe it or not, we're going to go all the way from starting with point sources to smearing things onto lines and panels, all the way back to turning things back into points. And that'll happen at the end of next lecture. It's really good to take something you're learning and keep returning to it. But in fact, there are some really important ideas in how you solve integral equations that are called Nystrom methods, which sort of go back and forth with these ideas of points and panels and lines. And the reason we're going to do that next time is because when you face a problem, it's one of the things you're going to have to decide about. It's one of the degrees of freedom that's not sorted out for you in the literature. You're going to have to pick. Is this a formulation I can use, Nystrom or point methods or line methods or panel methods? And is Galerkin important or not? Those are some of the things that if you develop a method for a particular problem you're trying to solve, you'll have to think through. And you'll have to decide which of these things will work for you and which won't. And some of them will and some of them won't. And so next time we're actually going to go back over some of these things, but first we're going to talk about quadrature. First we're going to talk about numerical methods for computing integrals. And then just so I'm set up for that, and since there are more of you here now than there were before, we'll also try and do the poll online. For doing the problem sets, which will start next week, I'll have evening sessions for that. If you have constraints about both Monday and Wednesday evenings, that you couldn't make either of those days, let me know. And if there are only one or two of you, I'll just arrange something. But if a lot of you do, then we'll switch days. Or if any of you want to, I'll offer a preference now about which days would be good. Anybody want to pick something other than Monday and Wednesday? Anybody have a different day? Tuesday or Thursday? Okay, well, so we'll probably start Monday and Wednesday, or maybe Wednesday of next week. We'll cover enough this week to do the first of the problems. And we'll just have the problem set sessions, and I'm going to, again, encourage you to come, because these problem sets, this is not about evaluation. These are, this comes very late in the term. It's much better that you get some experience trying to use these methods so you can decide if they're going to work for you for certain problems, because they're fantastic methods for certain kinds of problems and useless in other ones. So having you get through the problem sets and figure out how to use them, it's a toolkit you keep around. So come do the problem sets. We expect everybody to get through them. They come so late in the term, we can't ask you to really have a mastery of all the aspects of it. So it's much better that you pick up the big picture and you ask questions for the things we've left out in the lectures. We can't possibly cover all the details, but we do want you to be able to actually do some computations with these methods so you get a sense of how they work. So again, in the evenings, anybody has conflicts or issues about evening times, then let me know and we'll find some other ones. But then we won't start that till probably Wednesday of next week, but I'll get the problem set up so you can see what it is this week, and we'll do Nystrom next time. All right. Hopefully the video came out, the phone didn't die, and I'll post that too. All right, thanks. Thanks very much for staying. You don't have to stay for all of them. Did that? Oh, it's still there. Cool.